Hi everyone, I'm Laurent Hébert-Dufresne. I'm with the Vermont Complex Systems Center at the University of Vermont, and I'm here today to talk about how to best seed or start complex contagions in hypergraphs or network with higher order structure. And before I get started, I should really say I'm super excited to be here. This is my first Sunbelt conference, and while the talk I'm giving today is more focused on my own expertise, which is in mathematical modeling of contagions and network science, I think our results help us think more deeply about a lot of social issues happening right now, especially anything that has to do with bottom-up coordination in citizen organizations. So I'm really here looking for feedback, and even though it might be obvious that it's a pre-recorded talk, unless something went terribly wrong, I should be in the conference call with you all. So feel free to write in the chat if you have any questions, or if you'd rather wait for the end of the talk, you'll be able to reach me by email or direct messages on Twitter. I'm looking for feedback. I'm really excited to see what this community thinks about our work. Now, I should say most of this work was led by my PhD student Guillaume St-Onge, but also done in collaboration with the team behind the original simplicial contagion model, so Jacopo, Giovanni, Alain, and Vito. And I'll be sharing some of our recent work, so that most of it has to do with a new way to model analytically or mathematically contagions on a hypergraph. I think the model is flexible and super interesting in and of itself, but I'll focus on two consequences that we see in simplicial contagion. One is that even homogeneous groups can have dynamical heterogeneity. So things can look the same initially, but follow very different time evolution. And that's going to become clearer later. And then our main result, which is a consequence of that, is that for a lot of contagions, we ought to be thinking about influential groups and less so about influential spreaders. So groups over node is sort of the main theme of this talk. And if you're live in the Sunbelt session, you just heard from the man himself, Giovanni, presenting the simplicial contagion model. In my own words, this is a complex contagion model, meaning that your instantaneous probability of becoming infectious depends non-linearly on your number of infectious neighbors. The key part is shown here in panel H, which is that if multiple infectious nodes are found in the same group, then there's a boost, this beta triangle, in the case of a triangle, an increase in the instantaneous transmission rate of this interaction. The model makes a lot of sense to me because a lot of social reinforcement effects like peer pressure are group specific. So the higher order structure or the group structure of a network matters a lot. Previous mathematical description of this simplicial contagion model have used differential equation like the one shown here to follow the dynamics of the system. So we're tracking the fraction of infected nodes through time and summing over groups of different size that those nodes might belong to. And we're assuming that not only are all nodes sort of equivalent so that they follow the same equation, but that groups of a similar size have a similar state. Now that's a big assumption. It works fine if what you want to describe is macroscopic state of the system, so it captures the bistability and discontinuous transition shown on the right, but for real heterogeneous structures, we're going to need something more refined. And I know I'm preaching to the choir here when I say things like people are not homogeneous, and obviously groups of people are not homogeneous. But I want to illustrate and motivate our study using specific examples from US politics that show exactly that. One of my favorite studies is that of the electome from the Media Lab back in the 2016 presidential election in the US. So you can take networks of Twitter discussions, who follows whom, and you can color nodes based on who they follow. So if they follow only Trump, you put them in red, only Clinton in blue, both in purple, or neither in green. And what emerges is a block structure. And different communities can have very different structure. Different nodes can play very different roles. Obviously, you have central accounts here. You also have very peripheral account. To illustrate that a little more concretely, I really like the work of Sarah Jackson, Moya Bailey, and Brooke Foucault Welles. They have a book out this year in 2020 called #Activism or #Activism. And I really like their work because it illustrates the need to think about communities and groups when thinking about emerging political movement, especially when they emerge from the bottom up. This is a network from one of their 2015 study looking at the #MyNYPD on Twitter. So this was a campaign started by the NYPD, which obviously went wrong. People overtook the hashtag. And if you look at the network now, you're not necessarily going to realize or know who those central nodes are. So these are people with not a lot of followers that ended up being at the core of this hashtag movement. And we see the same, sort of core periphery structure here, where we have some very central individuals and a lot of heterogeneity, some people that are not central at all in the periphery. What I think is fascinating about this work is this result that there's barely no correlation and no significant correlation between the number of followers that an individual account might have and their influence in this conversation. Influence here being measured as the number of retweets and mentions for that individual account. So a correlation of about 0.145, not significant at all, which is kind of crazy because it clashes with the typical notions of influential spreaders. So if you're familiar with notions of influence on networks, the first order metric is always going to be your degree. If you want to seed a contagion in a network, you should seed it in central nodes and nodes of high degree, right? Here it's not what happens at all. This movement was taken over and the hashtag was dominated by people with very little followers initially, who became important regardless of their low degree in this original Twitter network. And in a nutshell, that's the result that motivated this study. I'm curious about whether having models with a more realistic notion of social groups, of higher order structure and network, and more realistic nonlinear model of contagion can help us understand why a lot of these social movements tend to emerge not around classic media units on Twitter or accounts with millions of followers, but often within tight-knit groups that don't have that much attention and yet are able to get a contagion going. So very simply put, our question for the rest of the talk is going to be, who are the influential spreaders of complex contagions on networks with higher order structure? And to think of influential spreaders, obviously we're going to have to consider heterogeneity. Not all nodes are the same, people have different roles. So we're going to look at the simplicial contagion model, and so far I've been very confused myself about whether I'm talking about groups, communities, blocks, or simplicial complex. And that's because in the mathematical representation we're going to use, those are all the same. For now, I'm going to try and stick with groups. So we're going to look at a bipartite networks where we have a heterogeneous degree distribution for how many groups a given node belongs to, which I'm going to call the membership distribution. And we're going to have a distribution for how many nodes are found in different groups. So that's the size distribution of groups. I won't go too deep into the math, but essentially, if you've seen heterogeneous mean field description before, this is very similar. So for nodes, we're just going to track the number of nodes that are susceptible or infectious with a given membership at all times. So this is this SM here, which would be the susceptible nodes with membership M at time t. For groups, it's a little different. We're going to use what we call an approximate master equation, which means that we're going to follow exactly the entire distribution of states for a group of a given size. So we're going to track groups based on their size and the number of nodes that are infectious within that group. So we know exactly how many groups are of size 10 with 0 infectious node, size 10 with 1 infectious node, and so on. So it's a fairly complex mathematical model, but it's easy to convince ourselves that it falls back on the previous coarse-grained descriptions by capturing bistability and discontinuity. So if we have a nonlinear contagion, meaning that this transmission rate beta that we make a function of n and I grows nonlinearly with I, so the number of infectious nodes in a group, then we can find discontinuous transition in the case of a power greater than 1, so superlinear transmission rate, where we'd have bistability and so on. Now, the reason why we want this more complicated model is to track some of the heterogeneous dynamics that occurs behind the scene. So on the right of the slide, I'm plotting the time evolution of groups of size n. On the x-axis, I show the number of infected nodes I in the groups, and on the y-axis, the distribution of the states. And for different times, as you go up this figure and into darker shade, what's really interesting is that even though we start with a homogeneous distribution at time t equals 15, at time 18, we get this bimodal distribution where about a quarter of groups now have an almost fully infectious population, while 3/4 are still mostly non-infectious. And so this bimodality would not be captured by the classic descriptions that average over all groups. But also it brings an interesting question forward, which is, can we maximize this faster mode? Can we make the contagion spreads faster if we understand where the heterogeneous dynamics comes from? And to do so, we're going to try and maximize the initial speed, so the derivative of I at time t equals 0. And we're going to look at two different strategies. We're either going to try and engineer the variables over nodes, so this SM, trying to pick nodes with the highest membership to be infectious first, or we're going to engineer the initial conditions over the variables that describe the groups. So here picking maybe larger groups to be infectious first. Here's a cartoon or an illustration of this problem. Now imagine that we want to start a campaign using a hashtag on Twitter, but we have a finite budget, so we know that we can only start or seed our contagion with 4 accounts. Well, the strategy on the left, the influential spreader strategy, would say that we want to start our contagion on accounts with the most followers, which in our representation means accounts with the highest membership number. But in terms of groups, that means that we're essentially infecting groups at random, but focusing on high membership nodes. Whereas on the right, with the influential group strategy, we're picking nodes at random, but now being smart about which groups those nodes might be found in. And that means that we can target larger groups or try and maximize and find the most profitable groups. And I know I was just very vague about what we mean by optimizing our initial conditions based on groups. The truth is, at first we had no idea how to do that, so we created a very complex optimization problem, because you can imagine that maybe infecting a large group completely gives you a very stable infection seed. So it's very hard for that seed to stochastically die out of the contagion if there's a large infection rate because of nonlinearity. Similarly, you could imagine that you might want to infect large groups about halfway so that you maximize the number of interactions between infectious and susceptible nodes in those groups. It was just unclear. Turns out there's a fairly simple solution to this complex optimization. So if you look on the right here in the box, I have this solution for what we want to optimize for, which is this R quantity. And essentially what this quantity is saying is that in a group of size n with I infectious node, the potential number of infections per infectious node is given by the number of susceptible, n minus I, that infectious node is going to be in contact with, times the transmission rate for that particular group, so beta of ni, and then divided by the total number of infectious node therein. So what this means is that what we want to maximize is the potential impact per infectious node for all groups. Now here's our main result. So we're using a network parameterized with parallel degree distributions for both sides of the bipartite network. So parallel distributions for memberships and group size. And we're going to look at what happens when we vary on the x-axis the non-linearity, so the exponent nu, of this contagion process. And on the y-axis, I'm showing the initial speed, which can be negative if the contagion dies out, or positive if it spreads. And we want to make it spread as fast as possible. And the 3 strategies are colored here. So in green, we have random strategy, infecting random nodes. The influential spreader strategy is in blue, and influential groups or simplices in orange. And what you see is that if the contagion is strong enough, so at nu about 2, there's this crossover where it's now better to target groups than influential spreaders. And eventually, at the end of my x-axis here, a contagion would die if we only pick the high membership node, but could survive if we start in groups in a smart way. So the more nonlinear a contagion might be, the more important it is to seed it using influential groups and not individual nodes. And that's sort of where we're at right now. This helps us understand why some contagions that are very nonlinear, meaning that to spread they rely on positive feedback and social reinforcement, might have a tendency to start not around nodes with the most followers or the highest degree, but nodes that are part of tight-knit communities where you really get the benefits of this social reinforcement and feedback. So this at least helps us understand this counterintuitive result from the Jackson and Foucault Welles paper, which is that there is barely any correlation between the influence of a node in a social contagion and its initial degree in terms of followers on Twitter. But beyond that, there's a lot left for us to do. So I just showed you that the classic influential spreader picture can fail. Sometimes it is better to ignore individual nodes and their degree and focus on groups and how big they are or what their structure might be. It's unclear when we need to do that. So it's a complex interplay between the network structure and the nonlinearity of the contagion, and we want to understand, what determines this trade-off. Once we get that, well, then maybe we can think about forecasting virality of memes, hashtag, and news. There was a great series of paper, 2015 onward, by Lillian Wang, Phil Manser, and YY An, looking at this problem of using community structure and nonlinear contagions to predict virality of memes. I think with more refined models now we can go back to these cool ideas and do a little better. We can also look at the inverse problem. What if we want to stop the contagion? What if it's misinformation, right? And then it becomes an immunization problem. Is it better to immunize central nodes or to immunize influential central groups? There's a lot to be done here. So just to wrap up, I think the key lesson here is that we're starting to have models that help us think more deeply about the interplay of higher order structure and nonlinear contagions. Complex contagion models go back over 20 years. And time again, what these models have done is shift the focus away from individuals and more towards group. But I think using our more refined model and using simplicial contagions, what we've shown here today is that when a contagion is nonlinear enough, meaning that it really relies on positive feedback and social reinforcement to spread, then we really need to think about influential groups and not influential spreaders. And this explains what we saw not only in our model, but on Twitter data using Jackson and Foucault Welles' work, that to start a conversation or to be influential on a platform like Twitter, it's not really about having the most followers or the highest degree, but more about being part of a tight-knit group that can be influential. So we're just starting to have some results out now. Guillaume has 2 preprints available, so you see the archive codes on the screen. I'm also putting my email and both my and Guillaume's Twitter handle on there. I think I already said it, this is my first Sunbelt, so I'm really excited to be here. I think this was a lot of fun, even if pre-recorded. So I'm really looking for feedback, eager to hear your questions and comments, because I think we can make this work stronger, and we'll be happy to share more work in the upcoming months. So this is really your chance to influence some of that and help us better understand this complex problem. So thank you.